Hello everyone and welcome to TLE Eliminators PCD for Leetcode's Weekly Contest 475. Today we'll be discussing all the problems from A to C. Okay, I think D was pretty hard today, as someone said. How was the contest, guys? How was the contest? How many solves? How many solves? And I guess most people would have solved two, I'm assuming. Did people solve three? Three was also pretty simple, I think. Up to solving three was very simple, and then fourth was like a pretty hard, so there was like a pretty big gap, I would say. Not many viewers today. Interesting. Anyways, let's get started with the problems. The first problem: minimum distance between three equal elements. Given an integer array, you need to find a tuple ijk such that nums of I is equal to nums of j is equal to nums of k, and then the distance is defined as the pairwise distances between all three. So I minus j plus j minus k plus k minus I. Return the minimum possible distance of a good tuple. If no good tuple exists, return -1. And then there's some examples. So here the good tuple is like this one and this one and this one. And the minimum possible distance will be 6. So that's the answer. And there's a -1 case also as an example. N goes up to 100. Okay, N goes up to 100. So yeah, D was pretty difficult today. I also could not solve it. I spent more than like 1 hour, right? I spent like 1 hour 10 minutes almost on D, and I'm still quite clueless. Okay, so let's go through all the problems one by one. So problem 1 is pretty simple, I would say. Basic brute force. So problem A, right? So the first thing you need to observe is that nums.length is less than equal to 100. So we can say that n is less than equal to 100. So we go of n cube solutions are possible, right? We go of n cube solutions are possible, right? And since the condition is very simple, it just says find ijk such that nums of I is equal to nums of j equals nums of k, and also the distance is minimized. What we can do is simply go through all possible tuples ijk, right? Since we have n cube time, just go through all possible ijk, try all possible ijk, right? And find the minimum one satisfying the conditions, right? The minimum one satisfying the conditions, right? We can directly just check the conditions, right? That nums of I equals nums of j equals nums of k, and then we can find the minimum value of this thing, absolute value of k minus I plus j minus k plus I minus j. One observation: if let's say you have your I, j, k like this, okay, so I, j and k, and then k is greater than j, okay, k is greater than j, also j is greater than I. So we're going to assume these two things: k is greater than j and j is greater than I. So what happens? We have we need to take this distance, and this distance, right? That's what absolute value means. Absolute value means distance of 2 points on a number line, right? So if you observe, this distance is simply equal to 2 times k minus I, right? Or in other words, we can write it like this. We can say that I minus j, right, plus j minus k plus k minus I, right? If we write this, and if we have the values k is greater than j greater than I, let's just assume this, then what will happen? We will have j minus I plus k minus j plus k minus I, right? And then this will cancel, and we'll get 2k minus 2I, which will be equal to 2k minus I. Okay, so for the formula, we just need to find the one with the minimum value of k minus I, right? Min value of k minus I, three values which are equal, right? So we simply check that with brute force. So let's have a look at the code. Pretty simple code. We'll just go through, set our answer as infinity because we're trying to minimize. Then for every I, for every j greater than the I, for every k greater than the j, if a of I is equal to a of j and a of j is equal to a of k, then we can minimize the answer. We can say ans is the minimum of ans and 2 times k minus 1, right? So we're just brute forcing all the cases and finding the minimum answer. If the answer is still infinity, then it's not possible. So we can return -1. Otherwise, we can return the answer which we found, right? So that's it for this question. Pretty simple. Let's move on to the next one, right? Okay, let's move on to the next question. Okay, so in this question, it's the same problem again. Given an array nums, we need to find tuple ijk such that nums of I is equal to nums of j, nums of k. Everything is the same, except the length is now 10th power 5, right? N is now 10th power 5. So now we need to solve it for 10 to the power 5. Okay. By the way, the time complexity for problem A, we can note it down that the time complexity is simply n cubed, right? Time complexity for problem A with the solution which I have described, it's n cubed, right? And now problem B is the same problem, but we need to solve it for we need to solve for 10 power 5, right? Problem B, we do same problem with n less than or equal to 10 power 5. So our expected time complexity will be big O of n or big O of n log n. Right? So how do we approach this problem, right? So let us think about the conditions again, right? So first thing we saw was our minimum value will be 2k minus I, right? So from the previous problem, our minimum value is going to be 2 times k minus I, where you can assume that this is the current index, right? And this is some previous index of nums I, right? So nums k, and there should be some index nums j in between, and then there should be nums I, right? So this is what we already know from the previous problem about the structure of this problem, right? So all we need to do is optimize it to be in n log n. Right, we need to optimize it to be in n log n. So how do we do that optimization? What we can observe is that for each k, so we are going to assume that we look for the k, right? So k is the one which appears latest. So k is the one which appears after j and I. So for each k possible, right? We need to find a previous occurrence. So this, the value of action k will be nums of k, right? So we need to find a previous occurrence. We need to find two previous occurrences. We need to find two previous occurrences of the same value or of nums k, right? So basically what I'm trying to say is, given an array like let's say you have 1 2 3 1 4 1 5 6 6 2 3 2, something like this, right? So assume that you're at this position I and you want this to be your k, right? Then you need at least two previous occurrences of 1, so that this can be chosen as k, this can be chosen as j, and this can be chosen as I, right? Then only it will satisfy the given condition. Similarly, let's say we were at this 4, right? There is no occurrence of 4 before, so we cannot do this, right? We cannot let this be k. Similarly, if we choose this 6, then there is only one occurrence of 6 before, but there is no I, right? We cannot find the first occurrence, so this will also not be a possible case. This will also not be a possible case. And what if we had, let's say, the last two, right? So if we chose this, then we can say yes, there's a possible occurrence of j and there's a possible occurrence of I, right? So we just need the last two previous occurrences of every element, right? Because we want to minimize the distance between them. So if we had, let's say, an array like this, let's say 1 2 2 1 1 2 1 2 2 2 1 1 1 2. Okay, let's say we had this, fine. Now if we take this one, right, and let this be the k, then ideally this should be the j and this should be the I. Okay, there's no point of taking j or I from anything before, because we are trying to minimize the distance 2 times k minus I, right? We're trying to minimize the distance 2 times k minus I. This is what we are trying to minimize, right? So it makes sense that at each step, if we assume that this is the k index, then the previous two indexes should be chosen as nearby as possible, right? So we just need the previous two occurrences of nums_i. So let's write this down as our observation. Our observation is that we need the previous two occurrences of nums_i. Previous two occurrences of nums_i, right? Does that make sense, guys? For B, does it make sense that we need the previous two occurrences, right? Okay, so how do we store this? What we can use is we can use a map, right? We can use a map. What we can do is we can have a map from the current value to the previous two occurrences. So to store the previous two occurrences, you can use vector or you can use pair, you can use q, whatever you want, right? So the way I did it was I did q. So from each position, I stored a queue, and this queue will have the previous two occurrences. Why did I use queue data structure? Because you can use pair also, it's fine, but it makes the logic easier when you have a queue, because whenever you push things to a queue, right, then you can push from the back and you can remove from the front, right? That's why I used a queue data structure, because we can push back and then we can pop from the front, and that makes sure that we can always keep the size of the queue as 2, right? So we'll ensure that size of this queue is less than equal to 2, right? And then what we can do is basically every time we have a new nums_i, or every time we find a nums_k, we can check if the size of the queue of that nums_k is at least 2, and then we can take the previous two occurrence of it and we can calculate our answer, right? So let's just write a pseudocode for this. So pseudocode, right? And what our pseudocode will be, it will look something like this. So first we define a map from int to q of int, okay, right? And now what we can do is we can have for each x in nums, right? For each x in nums, now first we try to pair this x with some previous value. So we can say that if map of x dot size is equal to 2, right? So we need at least two elements in the map. So we can say, we can write greater than equal to or equal to 2, doesn't matter, right? If map of x dot size is greater than equal to 2, then what we can say is, or let's keep it equal to 2 actually. Then what we can say is we can pair it with the first one. So we can do something like this. We can be like map of x dot, we can say ans will be updated with min of ans, comma 2 times this distance. So the distance will be the current k minus the I of the map. So we can say that map of x dot front, right? So this will what our answer will be updated with, and then we can simply push this thing to the queue. And we need to ensure that only 2 elements are in the queue. So we can pop if they are greater than 2, right? So that's it. And then once this loop is done, we get our final answer. We're basically maintaining that from every number, what are the previous two occurrences of the number we are storing, so that we can quickly answer for each index, what are the previous two occurrences, and we can update our answer. So that's it for this question. Because we're using a map, it will be n log n. But if you use unordered map, it will be big O of n itself, right? So let me just write the time complexity of this. It will be big O of n log n. Right? Makes sense? Any idea about fourth? To be honest, I'm pretty blank about fourth. Not gonna lie. So let's have a look at the code for B. Yeah. So n is the size of the array. Ans is set to infinity in the start. And then we have our map of into q. You can also have a map of into pair. That also works. But you need to handle some cases yourself. Okay. So if the current element exists in the map and it has a size greater than 1, I'm doing ans is equal to minimum of ans and 2 times I minus map dot front, right? So 2 times the current value distance to the second previous value. Fine. Now what I'm going to do is I'm going to push the current value to the map. If the size of the map is greater than 2, I will pop the first value from the queue, right? First value from this queue. So that ensures that only the last 2 positions are there at each step. And then finally, if the answer is infinity, I return -1. Otherwise, I just return the answer. Right, so that's about it for this question. Cool. This was problem B. Yeah. Okay, so let's move on to the next problem. Problem C. Thanks, Arpit. Let's move on to problem C. Okay, so problem C I felt was a pretty typical DP, but the constraints were pretty strict. So if you made even the slightest mistake, you would take extra time and you would TLE. So let's have a look at how to solve this problem. Okay, so given an m into n grid, each cell contains the values 0, 1 or 2. You're also given an integer k. You start from the top left and reach bottom right by moving only right or down. So far it seems pretty standard. Each cell contributes a specific score and thus has a specific cost associated with it. So if your cell has 0, it will add 0 to your score and costs 0. If its cell is 1, it adds 1 to your score and costs 1. If cell is 2, then it adds 2 to your score and costs 1. Now return the maximum score achievable without exceeding a total cost of k, or return -1 if no valid path exists. Okay, so we need to find the maximum score without exceeding total cost of k. If there is no path which does not reach here without total cost of k, then we will say print -1. Yeah, that's what it says. If you reach the cell before the total cost exceeds k, and the path will be invalid. Fine. And so there's some examples of path with some score. There's an example of a -1 case. Let's have a look at the constraints. Okay, so we say that mn is less than equal to 200 and k is less than equal to 1000, right? So let's have a look at the constraints. Problem 3. Constraints. Mn is less than 200 and k is less than equal to 1000, right? And the first element of the grid will always be 0. That makes sense because it just simplifies the problem, does not need us to give a cost for the first element itself. So the first element will always be 0. Cool. So how do we approach this problem? And I would just put a prerequisite for this problem, prerequisite to understand DP, because if you have never done DP before, I don't think you'll be able to do this. It's not a hard DP problem, but it's a decent level DP problem. So I'll just put a prereq on this problem that you need to know DP. Fine. Okay. So if you have done any dynamic programming problems involving grid, like if you do the top 10 dynamic programs in any list, you will definitely see the problem where you start at top left and need to go to bottom right in some grid. And you need to see some how many ways there are, what you can. The only list in this problem cost score, right? Usually we get a score and that's it. But here there's also to our score, and that's the twist of the problem. Fine. So what are we trying to solve? We're trying to reach from top left to the bottom right. For people who don't know DP, definitely go ahead and study it, right? So if you're getting stuck at C, then you should try learning dynamic programming. If you know any DP, then you would see this question and you would know it's DP. It's a very obviously DP type of question. Okay, so you want to reach from top left to the bottom right of the grid, and you want to find the path which maximizes our maximizes our score while keeping the total cost of the path as less than equal to k. So both the conditions should hold, right? Now the issue is, if we have a total cost, right, if we try to maximize our score, later on we'll see that the total cost of this path becomes too much. Okay, like if we're trying to maximize our score, we might later on see that the path cost has become too much. Like for example, if we had like let's say our path was something like this. Okay, let's say this was the grid, and then these were all zeros, right? And our cost was not that high. Our cost is like the minimum cost k is enough that, so I'll tell you abstractly, like the best solution would be to do something like this and then reach the answer, because to go through values of zero does not give any cost. But our solution might try to get a maximize our score, and then it would get stuck here because now the cost is too high, right? The cost is too high and it stops here. So that's why we cannot do it greedily. We need to do some kind of dynamic programming, because if we just try to maximize our score, we might not stick to this constraint that the cost is less than equal to k, right? So basically we need to find we need to find some path such that the cost is less than equal to k also, and this is why we are using dynamic programming to solve this problem. Cool. Otherwise with simply score maximization, it's not simply score maximization, right? We need to keep track of this thing, and this is the most this is the unique part of the problem. Okay, so when we have done the standard grid DP, we already have two states, right? The two states are I and j, right? So states, whenever we do a DP, there's four parts to a DP, right? Any DP, we have to think four parts: state, transition, uh, base case, and final answer, right? So these are the four parts to any DP. And let's think about these states. Okay, let's think about what these states are. So what is important when you're thinking about a state is to think that you're somewhere in the middle of the solution. Okay, you're somewhere in the middle of the solution, and somehow you have come to this position from the start till here. Now you need to wonder, okay, what are the things which are important for me to know so that I continue to the end successfully? Okay, so what are the things that are important for me to know to continue to the end successfully? And if you watch Eric To's video on DP, you will learn this kind of idea. He has like a 10-minute video and he does explain it pretty well. Basically, when you're in the middle of your DP, what are the things that matter and what are the things that don't matter? And whatever the things which are a matter, that is going to become your states. Okay, that's going to become your states. So obviously what matters is your position, right? Your position though definitely matters. So DP of ij is a given. What else matters? What else matters is how much cost it took me to reach here. Okay, what else matters is how much cost it took, cost incurred so far. Okay, the cost incurred so far, that's the third thing which matters, because if I have too much of a cost, I won't be able to go on any further, right? So the cost incurred so far will also matter. So we can write it over here as, let's say, C. Okay, C is the cost so far in some path till this state. Okay, so these are the three things which are important on the state. And what will our DP store? Our DP will be storing the max score. Okay, DP will be storing the max score to reach INJ if the cost to reach INJ was exactly C. Okay, so that's going to be our DP state. Let's write it down in English. So in English, you can say that, or in words, we could say that our DP state, our DP state stores the cost to reach I and j on the grid in the fashion they described, right? So moving down and right, starting at 0 0, having incurred a cost of exactly C. Okay, of exactly C. And that is the only three things which matter: where we are and what is the cost so far. And then sorry, and DP does not store the cost. It stores the max score when we reach, right? When we reach. So that's what our DP is storing, because the final answer is the max score, right? So our DP state needs to store the max score which we can reach to ij when we have a cost of exactly c. Okay. So now next thing we need to think of is how much memory or how much total space and time this storing all these states is going to be. Okay. So I goes up to, as we know, I goes up to 200 because m goes up to 200 and also goes up to 200, and the cost can be at most 1000. Okay. So the cost can be at most 1000. So we can write here that I is less than equal to 200, j is less than equal to 200, and the cost is less than equal to k, which is less than equal to 1000, right? And now if we multiply this out, we get 200 times 200 times 1000, right? And then this is quite high, I would say, right? 4 times 10 power 7. So this will barely be done in 1 second, right? So it will be done like about, it can be done in like 1 second, but your code needs to be pretty fast, right? There are a lot of states. There's a lot of states, lot of states, lot of states, but it's doable. But it's still doable in 1 second. It's still doable because 10 power 7 is doable in 1 second, right? Roughly, almost like up to 10 power 8 is sometimes doable if your code is like pretty like linear operations and not many complicated operations. So it is possible to think about this. But one thing this will make sure is, since we have such a high number of states, recursion will probably not possible, right? Recursion will not be possible, probably not, unless you optimize it like very much, I guess, because the recursive approach has an overhead of adding to the stack, right? So some people who would have tried doing from the recursive approach, the thing is each time you do a function call, it gets added to the function stack and then it gets removed. So that's how it's implemented internally in C++ or whatever language you're using, right? So recursion has a higher overhead, so it might fail if you try to use recursion for this problem. You must do like bottom up DP, iterative DP itself, right? So recursion might not be possible with this kind of high level constraints. Okay. Now let's try to think about the transition. Okay. Let's think about the transition, and the transition will be pretty simple only, I think. Very standard transition once you have the state transition. Okay. Let's try to focus on some cross section of the grid. We'll focus on a cross section of the grid. And let's say this is our current state. Okay. This position here, this is going to be a current state, dp, I, j, and cost. Okay. Now, obviously, we came here either from this direction or this direction, right? This using a down operation and this using a right operation, right? So basically, this is dp of I minus 1 j, and then this is dp of I j minus 1, right? And now we need to know what is the cost, how the cost has changed when we moved from here to here, correct? So basically, if my current value, if this value, if a of I is equal to 1 or a of I is equal to 2, then what happens to the cost? The cost will be simply minus 1, because now we have an extra cost, right? So basically, we have come from dp of I minus 1 j c minus 1 to dp of I j c if the current value is positive, right? If a of I is positive. Otherwise, we have come directly from c itself, right? So if else, if a of I is equal to 0, right? If a of I is equal to 0, then we can say that this has come from the same cost, right? The same cost, the cost has not increased. Okay. And also in both the parts, we need to maximize, we need to choose the one with the maximum score. So we'll just choose the one which has come from whichever direction gives us the maximum answer, right? So either we came like this or we came like this. So we'll just take max of them. So let's just write this logic down. We can write this logic down. If a of I is greater than 0, right? If a of I is greater than 0, then we can say that there will be the cost of 1 will be incurred, right? So we can say that dp of I j c is equal to the maximum of the two possible ways. So I minus 1 j c minus 1 and I j minus 1, c minus 1, plus the value of ai, because obviously the value of ai will get added on to our answer, right? So this is if ai is greater than 0. Otherwise, if ai cost will be the same from where we came, right? So it will be max of dp of I minus 1 j c and dp of I j minus 1 c, and there will be nothing added because ai is 0 itself. So this is our transition, right? So that's it. This is our simple transition, and as you can see, the transition is very straightforward. Only basic operations, addition and one max operation we are doing. So the transition is also pretty simple. It's big O of 1 transition, right? This transition is big O of 1, big O of 1 transition, right? So the number of states is n into m into k, and the transitions are big O of 1 using all basic operations. So even if it's 4 times 10 power 7 states, since we're using all the basic operations, the transitions will not be much. Okay, right. What else do we need to look at? Right now, so we need to see the base case. It's already given that grid of 0 0 is equal to 0. So what we'll do is we can just set our grid of 0 0 is already equal to 0. So we can just set our dp of 0 0 with a cost so far of 0 as having a score of 0, and then everything else will be set to negative infinity, since we'll say that it's unreachable so far, right? We want to maximize the score, so we'll set everything else to negative infinity and dp 0 0 to 0, and this will be our base case, right? And our final answer will simply be the number of ways to reach dp of n minus 1 m minus 1, and the cost can be anything. So the cost can be anything. We just want the maximum score, right? So we want the maximum score to reach n minus 1 m minus 1 with any cost less than equal to k. So we'll try all the costs from 0 to k, right? So whichever gives us the maximum score, here, max, right? Or we can say max of c less than equal to 0 less than equal to k, and we can write c over here, right? So this is our final answer. So we went through all the 4 steps of dp. We found the state, transition, base case, and the final answer, right? All is left to implement. We argued that the state depends on 3 things: our position and the cost so far, and also we showed that the states are doable in 1 second. We showed that there's a big O of 1 direct transition, right? Big O of 1 direct transition here, and then we showed that the base case is simple, the final state is simple, and one thing we can do is our transition we can write a bit neatly. So this ai greater than 0, we can simply like this minus 1 is there, right? This minus 1, we can just combine these two states, like these two transitions, into one transition. Instead of doing minus 1, we can do minus, like this is just for implementation. We can say that c minus ai greater than 0, right? So here also we can write c minus ai greater than 0. So this will help us write it as a one liner, right? We can write it as a one liner, or we can write ci equals min of a of I 1. This also we can write. This just helps you write it in one liner instead of writing if else. So it saves some time while coding. That's about it. It's pretty standard dp. Just you need to be efficient. You need to make sure that you don't use recursion, because I think recursion might TLE. Also, you should make sure to store your values in the heap and not the stack, okay? Because there are a lot of values. So store the dp table on the heap and not the stack, okay? And not the program stack. Why? Because when you have large dp tables, if you store it in the program heap, what happens, like you'll have enough space, right? But the program stack might not have space, might memory limit exceed if you try to store in the program stack. So make sure that you either use vector or you use global array okay? Do not try a local array. A local array will be stored on the stack. It might mle or it might tle, okay? So that's why you need to use a vector or you need to use global array. On Leetcode, I think it's better just directly use vectors itself. Fine. Global array, I'm not sure if it'll work on there, like multiple test cases or whatever. I don't know how Leetcode handles it. So it's best if you use a vector, fine, for your dp table. Let's just see. So how was the explanation? Was it fine? I'm assuming some standard basic DP knowledge while explaining this. If you're not following, then you should definitely like study a bit basic DP and then come back. DP in grids. Yeah, standard DP in grids. Please start with memorization explanation. I do not do memorization actually. Like, um, I don't even think in terms of memorization, so it's very hard for me to explain memorization. Plus, in this problem, if you try to do it recursively, it's very hard to not get TLE also. Why not score is a state? Score is not our state. Score is our answer. That's the maximum thing which we're doing. Oh, you got recursion with AC with recursion? Okay, fine. But it is risky to try recursion on this, I would say. Especially if it was on code forces, they usually have very tight constraints. On Leetcode, they might not have that much tight constraints for recursion. If you want to practice DP, there's always the CSCS set, right? This will cover most of your like basic patterns, especially like grid ones. Just solve like the first 10-ish. If you go to grid paths, very standard, like similar kind of DP, right? You have to find a path from the top left to bottom right, count how many paths are there, stuff like that. Once you do those kinds of DPs, the grid DP is very standard, right? Here the grid DP just has a cost, so your path cannot get more than this cost, so your cost also just becomes another state. That's it. Can I solve ICPC preliminary round questions? Not sure. I'll put it as a suggestion for TLE, if they want to host something like that. How was the prelim round for ICPC, by the way? Anyways, let's have a look at the code. Let's have a look at the code for this. The code is also pretty simple only for this one. Okay. So here's the code. N and M are I'm just taking as the dimensions, a dot size and a of 0 dot size. And I create a DP vector, right? So it's a 3D DP vector, n into m into k. I'm setting everything to negative infinity. Okay, negative infinity. I'm setting it to int min by 10. Why int min by 10? Because sometimes when you add stuff, you don't want overflows, right? So this is going to be my negative infinity. So n into m into k plus 1. Why k plus 1? Because the cost can go from 0 to k, right? That's why I need k plus 1. Also, dp of 0, 0, 0 is 0, as we discussed. That's our base case. Fine. Now, for every I and j, and we don't want to see 0, 0. So, for every I and j and every cost, either I came from down or I came from right. Right? I came from down or I came from right. Make sure that you're not taking out of index. So, that's why this condition is there. Okay. So, dp of ij c will obviously be the max of itself, and dp of I minus 1 j c minus this thing, so c minus the cost incurred plus a of ij, right? So that's the condition for this one. And similarly, to come from the right side again, if j is greater than 0 and c minus the cost incurred is greater than equal to 0, then dp of ij c is equal to dp of ij minus 1 c minus this cost plus the new score which is added on, right? So pretty standard DP, I would say. And finally, to print the final answer, so for everything in n minus 1, we'll try all the costs. Whatever gives us the maximum cost, that will be our answer, and we can return it, right? So pretty simple, straightforward DP. Only two cases: either we come from down or we come from the right, and the cost incurred can just be stored as a state. The score is obviously our final answer, right? At most, this would be 1500 or 1400 on CF, I think. Problem 4 today will not be covering problem 4, guys. I couldn't solve it, and I'm actually generally like I have no idea how to proceed on problem 4, to be honest. So I guess today's problem 4 was pretty hard, right? Even if you see the ranks, there are very few people who got all 4. Like some 23 people got all 4, so it's not very. It's not a typical Leetcode problem 4. It's pretty hard compared to a typical Leetcode problem 4. So yeah, we won't be discussing problem 4. How was the ICPC prelims? Did anyone give it? How many questions did you solve? Yeah. So before we end the session, I'd just like to inform you that our competitive programming courses, our self-paced courses, are live right now, and they are across 4 different levels. So they teach you from all the way from the basics of C++ all the way to number theory, combinatorics, dynamic programming, right? So if you want, you can check out Priyansh's video on what level is right for you. But we have a level for everyone, right? All the way to expert on CF, we have a level. Like if you finish level 4, level 1 through 4, then definitely you have all the knowledge required to be an expert on CF or even a CM, to be honest. So yeah, each course has more than 40 hours of recorded lectures, more than 100 practice problems, hints, video solutions for all the problems, as well as doubt support, right? Which is available almost 24/7. So do check it. I would, for the amount cost, the reward is very high, right? The amount of learning for only this much cost, I would say the return on investment is very high for a course. So really check if you haven't already. Okay. Right, makes sense. We could solve 4. So my team solved 4 questions in ICPC. 5th one we almost got, but time ran out, I guess. Yeah, it was a bit ad hoc, I would say, this time. There was not much data structure type of questions in the first 4 at least. But yeah, it is what it is, I guess. Decent contest. All right then, everyone. That brings us to the end of the session. That brings us. How do you solve the third XOR problem? That one was. I made the observation that the only bits which are getting affected by C are the last bits. So you can left shift your numbers and until the last bits get compensated. That's pretty much. To be honest, it was very intuition based. Like for a while I was completely stuck, and then suddenly I got an idea, and then after that it was very simple, right? The XOR problem. So yeah, it was kind of constructive ad hoc type of questions. Basically you realize that the value of C, right? The value of C is just flipping the bits associated with C with the XOR. So to do that, you can just move everything to the left. You can left shift everything A and B, so then it won't interfere with the answer. The rating of question 4 in today's Leetcode, I would say the question 4 in today's Leetcode will be at least 2000, because after spending an hour I didn't get it. So it should be at least 2000. I'm not sure how it would be. It's quite unusual, I would say, because there are very less solves also. Usually I see at least 100 solves or more. Usually there's like 500 solves on D. So today there's quite less, right? 20 solves on D. So I would say it's pretty hard. Okay then, guys, that's bring us to the end of the session. Pretty short session today, only 3 problems, but yeah. Thanks for watching and see you in the next session. Bye bye.